So we started with the monolithic application architecture. So this is a very familiar model. And now at the center I have an Apache Tomcat server. And I have a war deployment there. Now inside of that I have a storefront UI. I have an accounting service, inventory service, and shipping service. Now there's a lot of problems with this model, right? So if I have many engineers who are working on the same application, maybe I have 1 million lines of code. If one of those engineers makes one line of code change, you have to deploy the entire application to production. Right? So that becomes a very inefficient model at scale as you get larger and larger, and it's going to really slow things down. And so this adds a bunch of cultural problems, not just technical, which slow us down when we put applications into production. First of all, it's going to slow our velocity getting into production, right? So if I have 1 million lines of code, I make one small change to that application, I have to deploy everything to production. It also takes way too long to ramp up new engineers, right? So it's not so easy just to add new engineers to a project to go faster. We all know that because they're going to have to coordinate a lot more, and they're going to have to ramp up so that if that code base is 1 million lines of code, it's going to take them maybe a little while, depending on the engineer, to get ramped up and start making changes. And so it's really going to slow things down. At some point, that code base is really just too large for any one person to fully comprehend. So you might have people in the organization who were there from the very beginning, who maybe designed the application, and now what they're doing is they're being historians, telling the history of the code base. All of these special snowflake situations that brought down the production application, they're having to go and talk to junior engineers, new engineers on the project, to tell them the history of that code base and whether or not they can make a certain change. And that's really going to make these very productive engineers not so productive. Now we also have two opposing forces with this model, right? So maybe I have a DBA team, maybe I have an ops team, and I have my developers, right? So I hire developers to make changes to the application. And then I hire ops people kind of to resist that change. And so we have these two opposing forces that we have to go up against when we develop software in this model. One's an immovable object, and one's an unstoppable force. And it kind of ends up looking a little bit like this. Where you have your developer making changes and your operator kind of resisting that change because there's just so much complexity in that application. And if you have 20 teams in parallel making changes on that same production application, the ops team's going to have to worry about all of those changes and whether or not it's going to keep them up till 3 in the morning fixing a certain problem in production. So there's a ton of operational problems that we get with monoliths. First of all, it's going to cause us to coordinate a lot more, right? So we're going to have to coordinate our releases that batch changes together. And that's really going to slow us down because all of our teams are, again, building changes on this application in parallel. Also, our operations team is going to drive the runtime environment of the application. So if I have developers who want to use a new tool or upgrade maybe to a JavaScript framework or to upgrade a Spring Boot application, maybe I need to submit a ticket to my ops team to upgrade that virtual machine, right? And so that's going to take a lot of time because these operators are primarily worried with making sure that the application stays online. So all of these tickets that they get, they may be working on one, and then all of a sudden there's a fire in production, they have to go put that out, and so that's really going to slow progress down on upgrading those virtual machines. So our operators are going to take on the full operational responsibility of our application, including VM upgrades, and they're going to have to do that, and they're going to have to coordinate with developers to make sure that the production application is getting changes on time. But the main problem with a monolithic application, the reason why microservices are popular today is this. You have to deploy everything at once or nothing at all. Now, on our way to microservices, we stopped off at this beautiful model called the SOA, Service-Oriented Architecture. And in this model, we've gotten a little bit better. We've split out that deployment into now 3 separate deployments. I have the accounting service, I have the inventory service, and I have the shipping service. Now, at the very bottom there, I have my domain language. These are the objects that I'm going to use. I'm going to exchange between these services to implement a certain use case. Now, what ends up happening with this model is I have all that complexity there down at the bottom because I'm sharing libraries across these services. So what ends up happening is if I make a change to, let's say, the customer record there at the bottom, then I just deploy the accounting service, no harm done. But if I change the address record, what ends up happening is I have to deploy all 3 of these services at the same time. So now I have a coordinated release. So things have become more complex than the monolithic application where I just deployed a single app. Now, we've arrived at microservices, and we've gotten a little bit better at some things. Now, in this model, I'm going to have small teams organized around business capabilities, which means maybe I have a team of about 8 to 10 developers, and they're focusing on a very small use case. And they're going to integrate with other services through APIs. And so maybe I have 20, 30, maybe 500 plus microservices in the case of Netflix. And these are all small teams who are able to independently deploy features in parallel. Now, they gain independent deployability because they're no longer sharing libraries, which is pretty convenient. Now, if they're versioning their APIs, they can make sure that they have backwards compatibility with all of their changes, so they're not breaking their consumers. Also, as a developer, now I get to use the best tool for the job. So I'm going to build my application, and I'm going to run it in production. So if I want to use, let's say I want to use MongoDB for some reason, I can go ahead and do that. I can just provision that on my own, and I can run it in production. And now we're going to produce and consume APIs. And so we have to be a bit careful with this model because if everybody's kind of going at their own speed making changes, it's very easy to break a consumer. So we need to kind of change the way that we do testing so we can use something called consumer-driven contracts to do continuous integration to make sure that I'm not breaking my consumers. Now, we have to worry about something called eventual consistency in microservices. Now, everybody kind of thinks that eventual consistency in microservices is kind of a guarantee. It's not a very good guarantee, right, because we lose consistency, but it's not actually guaranteed. And that's because eventual consistency, let's say we have a transaction that spans multiple services, and something breaks down along the way, well, I still need to worry about rolling back state, right? So eventual consistency means that the system will eventually get to a consistent state. Now, if it gets to an inconsistent state and stays there, then it's not eventually consistent. So inconsistency ends up happening all the time in microservices, right? And especially if you don't have event-driven microservices, maybe you don't have some messaging middleware there to allow you to exchange messages, so you're just using HTTP. Now, this is pretty dangerous because what could end up happening 10 years from now, maybe you don't recognize a certain defect that's been caused by this inconsistency. What ends up happening is that in a warehouse somewhere, inventory keeps getting reserved, right? Because in the order checkout process, maybe a payment fails, and that inventory didn't get unreserved for maybe 1 out of 10 times. What ends up happening is that you have a literal Stack Overflow in a warehouse somewhere in Tennessee because you didn't really know that you didn't have eventual consistency as a guarantee. And so it's very dangerous to kind of do that without worrying about it. So in a monolithic application, it was pretty easy, right? We had a database, and as a developer, I didn't really have to worry about transactions too much. I didn't have to worry about consistency too much because the database would just handle it. If something went wrong inside of a transaction, it would go ahead and just roll back. Now, in microservices, I have to take on all these new competencies to be able to roll back state if it's inconsistent, right? Now, a question I get often is this a monolith or is it a microservice? And the rule that I like to give is this: if it takes longer than a day for an engineer to ramp up, it's probably a monolith, right? So it's not really about the lines of code. It's more about the ability of an engineer who's new on a project to start making changes rapidly. So the project should be easy enough to understand that that developer, by the end of the day, can ship changes to production. All right, so I'm going to walk through quickly an online store example. So in this online store, it's kind of like Amazon.com. I'm going to have about 5 microservices here. I have the catalog service, the account service, inventory, shopping cart, and the order service, and they all have their own database. They all have their own team of engineers. Now, I'm also going to have these front-end teams, which I guess you could call a microservice. And this is the online store web at the top, a Spring Boot application. And they're not really supposed to go directly to the microservice, right? So they have to go through some kind of application, an API gateway. Now, we don't want our front-end developers worrying about where a certain microservice is. And so we need to also build in these services to help communicate with the backend, right? So I have here what's called Spring Cloud Services, and in the center there I have a red application. That's the edge service. So whenever I get a request in from the front end, I'm going to go ahead and route a backend request to the service that I want to contact, and then all the way back up to the top. So it looks like for our front end developers, they're developing against a monolithic API, when in actuality, there's many microservices there in the bottom layer. Now, if you're going from a monolith to microservice, some advice. This is really the popular method of doing it. It's called splitting the monolith, which was presented by Sam Newman in his book, Building Microservices. And the idea here is that you're going to take your monolith and just cut away slices of it and turn them into microservices. Now, the first step here is to move all of your front-end code to a stateless application. So I have an online banking application. Now, all of my front-end code is now going to communicate with my back-end over an API. So that's the first step. And then the second step is to look at my database schema here. I have an account table, customer, and user. And I have to decide on which one of these tables I want to slice out as well, because each microservice is going to have its own database. And that means that I'm not going to have a DBA somewhere having to vet all of the changes across 500 microservices. Each development team on a microservice will have their own database. And so what I can do here is I can find the table that has the least complexity that I can just rip out, which actually isn't very easy. People have done it and been successful, but in practice, it's not so easy. And so there's other ways to do this, like building a legacy edge around that application and slowly building new microservices around it. And that's called strangling the monolith. So why do we need events with microservices? Now, microservices introduce a host of problems as well. First of which is that there's no foreign key constraints between services, right? So if something happens where maybe I remove an account record and there's a graph of objects connected to it, I have no foreign key constraint that's going to tell another service, if I delete an account record, to perform an action, right? So in a database, we have that. We have that consistency. And so now we need to use events to be able to do that. So when I delete a record, it's going to send out that event to other services that they're subscribing to. And they can go ahead and take an action, and then eventually they'll be able to be consistent. Also, a lot of people don't think about this very often, but in practice, you also have something called a data warehouse. And you might have a bunch of these ETL jobs running back and forth from the system of record to some third-party system. And you have to worry about that too, right? So you're going to have to refactor these jobs to point to the right microservice. Also, distributed transactions are very brittle, right? We might have a network partition, and so we need to really build in redundancy inside of our application. So using events, I'm going to be able to have a log of all of these little transactions and what's happened inside of these transactions, and I can use that to roll back state in the system, especially when the network fails. So in the end, distributed systems are very hard, right? So if we take on microservices, we really do have to learn a lot of new things, which we didn't have to do when we had a monolithic application. So without an event-driven architecture, your microservices really will end up drowning you in hard problems that you never really knew existed, because you'll never know why things went so terribly wrong, right? So going back to this model. There's going to be things with this model, cultural problems that you're going to run into as well. So there's a lot of things we have to take on now. All right, so event-driven microservices. Now I'm going to walk through an example of using something called Spring Cloud Stream to build an event-driven microservice. We're going to have a single microservice. It's going to be an account microservice, and we're going to use CQRS, which means that we're going to split this microservice into two separate sides, a query side and a command side. Now, this is what it's going to look like. So here I have a command service, which is a Spring Boot application, and that's going to be writing to an event store. Now, here I have Apache Kafka. I could use RabbitMQ as well. Now, with Spring Cloud Stream, which is very interesting about it, is that you can have these binders, which allow you to just change configuration to switch to a different messaging middleware. So maybe I can go from Apache Kafka to RabbitMQ or vice versa. Maybe in my development environment I want to use RabbitMQ. I can just change it in production over to Apache Kafka. And so as it's writing events, it's taking in a request like create an account, writing to that event store, and then we'll have an event processor. The event processor is going to be listening to that event store for these events, and then it's going to perform an action. And the action it's going to perform is to update a model incrementally. And so it's going to write out that account for the account event to the data store here, MySQL. And then on my front end, I'll be able to contact the query service, which is going to expose an API to allow me to fetch those queries. Now I can actually ship this in two applications, right? So this diagram I like because it shows you that you have an event processor. Now you can certainly have three separate applications here, but if you want to ship this as a command side and a query side, you can certainly do that. You'll just bake the event processor inside of the query service. All right, so now I'm going to go ahead and build this. So I'm going to go to start.spring.io, and here I'm going to choose, let me refresh. I'm going to name this the query side, command side. And I'm going to go ahead and choose a few things. First of all, I need a REST API, so I'm going to choose web here. And that's going to allow me to expose a REST API that will take in commands, right? And commands are going to write, queries are going to read. So I need web. And then I also need Spring Cloud Stream. And I'm going to use Stream Rabbit here instead of Kafka because it's easier to set up in my development environment, certainly more easy for demos. So I'll go ahead and choose Stream Rabbit. So I'll go ahead and generate the project. And because I don't have a ton of time, I'm just going to show you the finished project here. We'll walk through the code. So on the command side, you guys can see that, we have a couple things here, right? This is an account service, so I'm going to have an account object. I'm going to have an account event. That's going to contain an account, and it's also going to contain a timestamp. Now in my application class here, I'm going to have a few things. I have my command-side controller, and that's going to expose that REST API that's going to allow front-end developers to create new accounts. And I'm going to go ahead and inject in something called a source. Now this is a Spring Cloud Stream component. And this is going to allow me to send along messages to an output channel. Now if I go to the source of this, we can see what it looks like. Now this isn't in my project. This is in the Spring Cloud Stream library. But I'm going to use it. And it's going to allow me to inject in a message channel called output. And it's going to auto-configure this for me so I don't have to worry about it myself. Now the thing that I do have to worry about is giving it a name. So in my configuration here, my application properties, I'm going to go ahead and I'm going to say the output channel should have a destination name of an account, which will be the topic or the queue that it's going to send messages to. Now going back to the application class, I have the create account method here, so it's going to be a post request, and I'm going to go ahead and provide that account model. And that account model is going to contain a first name, last name, and account number. Now, because when I write to the command side, I'm not going to get a response back immediately, I'm going to basically just write and forget. I'm going to have to worry about an ID to track this object. And so I'm going to go ahead and randomly create a UUID, and that's going to allow me to then call back to the query service to see that that record was created. Now going back to the application class here, I'm going to go ahead and use that source to send along that event that I've just created from a REST API. And then I'm just going to return back that account event, which contains the UUID. So let's go ahead and do that. So I'm going to start this application up. First of all, I have Rabbit up and running. And then I'll go ahead and run this with Maven Spring Boot Run. So that's started up on port 8080. And before I check anything there, I'm going to go ahead and start building my query side. So this is up and running. And for the query side, if we go back to the diagram here, I'm going to have that event processor, which is listening for these new account events, and it's going to then write to the data store, save that account record, which then I can query through the query side. So I'm going to need a few things here. I'm going to need a database. I'm going to use Spring Data JPA. So if I refresh start.spring.io, same thing. I'll choose web, and then I'll choose Stream Rabbit. And then I'll also choose Spring Data JPA, and H2 will be my database. Then I'll generate the project, and of course I have the finished product here. So if I go back to my IDE, I have my query side, and it's going to look very similar. So I have an account, right, and that account is now an entity, so it's a JPA entity, which has all the same fields, properties, except I have an internal ID. So it has that account number. And then I have my account event, which is just going to wrap that account. Now in my application class, very similar again, I have an account controller here. This is going to be the read API. So whenever I want to read a model, I'm going to request from this service. So maybe I want to get the account by its account number. and it's going to go ahead and use an account repository to look that up. So very simple, and that's at /accounts. And then things change a little bit, right? Because now I'm a consumer, I'm a subscriber, so I need to actually just listen for events, whereas the command side was publishing, now I need to subscribe. And so here in the event processor, I'm going to enable binding, and I'm going to specify that I want to use a sink. Now, I can use a sink or a source or a processor. And for the sink, it's going to just monitor, subscribe to the input channel here. Again, this is with the Spring Cloud Stream library. And so once I've enabled that binding and added configuration, it's just going to automatically configure this class to start listening for these events. And to do that, I'm going to go ahead and add an annotation here called stream listener and specify that I want to listen to the input channel of the sink. Now, every time I receive an event, I'm going to go ahead and log that out to the console. And then I'm going to go ahead and save that using the account repository that I just injected into this class. So I'll get the payload, and then I'll get the account, and I'll save it. And then that's the full workflow. So if you can imagine it, we're just writing on the command side, and then on the read side, we're just subscribing to these events, and then we're performing an action. Now, this is a pretty trivial example. I've built pretty big reference architectures that contain state machines, which will actually perform a certain action in response to the state of an object. And that'll be just like a status field, like account created, account confirmed. But this is a pretty easy example to see how the workflow works. So now I can go ahead and start this application up. Before I do that, I do want to show you that I also have configured this query side to listen to the destination account. I've also said that it should be durable, so if something goes wrong, that it should retry. So I'll go ahead and start this up. And that'll start on port 8081. And we see everything worked. So now I can go to my REST client here, and I'm going to go ahead and I'm going to post a new record here, which has my first name and my last name, and I'll send. That's going to create an event, send it to the query side, and to be able to see what happened there, I can go ahead and just copy this GUID, and I'll use that as my reference. Before I do that, let's go ahead and look at the log output from the query side. So we can see that the event was received, and we can see what the payload is. So that means that it received the event, and it was able to save it to the data store. So now I'm going to go to the query side here, and I'm just going to replace this GUID with the new one, and this is on 8081. And just go ahead and make a GET request, and we can see that it was able to write that to the database. And so that's it. That's basically CQRS with microservices. It does get pretty complex. I do have these full-scale examples that show you how to use state machines, and so I'm going to walk you through what that looks like now. Also, you can slap an API gateway on top of it, right? So we talked about the API gateway earlier. That's going to expose this as a single microservice, right? We want to make sure that our front-end developers are able to consume these APIs in the same way that they would normally. We don't want to have to worry about this command-side, query-side stuff. And so we can use this edge service to simulate what a monolithic application will look like. So a few guidelines here. So domain events are going to be first-class citizens of this architecture, right? So every time you change state in the system, you'll have a domain event, which will then go ahead and apply that change to the query model. So our domain events are going to have a subject, and they're going to contain immutable data. And that's going to look like something like this. So here I have my entity, and this is a project event. And I have a subject, which is my project. And then I also have a payload, which I didn't show you earlier. Now, that immutable payload is just going to be a map. And it allows me to really put anything I want in there, right? So I'm not going to actually have a class to serialize and deserialize. I'm going to use a map here, and then I can send along anything that I want. Now, every domain event is going to apply a state transition to an aggregate, right? So we looked at the account earlier. Now, that's going to be an aggregate object. It's going to have a status on it. Every time an event is processed, it's going to change that state, right? So here I have a state machine where I have an order created event, and that's going to go ahead and change the status to account connected. So event sourcing stores every state transition as an event in a log. And what that looks like is this. So if I had that account object, I want to make sure that that event log's accessible. Now, I didn't store those events in order earlier, but I'm going to want to do that in a production application. And I want to expose that to my developers via the API, because I want them to see how states change in that system. I also want to be able to recreate state. Maybe in the future, I want to create a new model. So I can go ahead and I can process all these events in order and create a new model from that. Now here's a video of what a state machine looks like as it flows through the state machine. So here we have order events being processed, or rather this is account events, or order events. And we can see that it gets to a terminal state there at order succeeded. This is what I mean by eventual consistency, right? So if you have something like this, then you're eventually consistent. Because if anything fails along the way, then we know that we have to perform some operation to roll back. So I'll show you that again. Oops. Go. All right. And we can see that it's going to that terminal state. Now, if something failed along that path, it's going to go to order failed. And then we can go ahead and we can unreserve that inventory in the warehouse, not have to worry about that Stack Overflow in that warehouse 10 years later. So event-driven microservices, you also want to build hypermedia APIs. That's going to allow you to embed links in each one of these responses. Then you can go ahead and get the event log, or you can get the commands as a part of that object. So here I have an example of a project record that I've returned, and I have my hypermedia. So I have my, so the project was just created, and we have the links there, and we can see that I have my commands. And so if I am a consumer, I can just go ahead and see what the commands are that are available for this project. I can also see that log of events that are going to be in order. And so here's that log of events. We can see that they're in order, and we can see exactly what's happened. So commands are going to generate events, right? So here I have maybe I have a command which is create order, and we can see that it's going to transition the state to account connected. And right, so commands are going to generate these events, and these events are going to change the state of the system. So we've gone from order created to account connected because we had an order create order command. So our command generates an event, and that's really just this balance between command and event. A lot of people think that an event is a command, or command is an event, but really commands just generate events. And commands are going to be attached to your aggregates. So here again, if I go to /projects 102 /commands, I'm going to be able to see what the commands are that are available to be performed against this object. And we see that I have one command here. If I make a request to that, so I have the commit command, then I can go ahead and process that command. So event handlers are going to subscribe to an event and apply state changes to an aggregate. So here's an example of this is actually a Lambda handler. So you can actually add in things like serverless to be able to handle events and be able to perform some action. So here in this activate account handler, I get in the event, and then I'm going to go ahead and get I'm going to call back and get the most recent event, and I'm going to make sure that the account is not already activated, right? So then I can assert back that exception back to the front end and say, you've already, that account's already activated, you can't apply that command, right? Because if we have duplicate events, right, which can happen, we want to make sure that those duplicate events don't get the system in some inconsistent state. So we have idempotence, which means that I'm only going to process one event, it's going to change the state of the system, and I'm no longer going to be able to process that event again. So event handlers are going to look like nodes on a directed graph. So here in the state machine, we can see that each one of these event handlers is going to perform that action, right? It's going to monitor for that event, perform an action, and then it's going to transition the state. So we can see what those event handlers look like here. So since I know how I got here, I know how to get back, right? So that's the whole idea in a distributed transaction. For each one of these event handlers, I know exactly how to get to the final state that I've arrived at. So I know how to go back, right? So I can rewind these transactions by appending more events to fix this transaction. And then events are just edges on a directed graph. So we're going to trigger a command here at account connected, right? That's a handler. And then I'm going to have that event that's generated, and that's going to go on to the next handler. So event handlers can generate the current state of an aggregate, right? So every single event handler there is transitioning that state. It's going to create a command that will be subscribed to by a different handler, and we are able to make sure that our transaction is consistent. Going back to that video, transitioning to that final state, order succeeded. Now in this UI, this is a reference architecture I created. We can see there that I have my commands. Now I've used Hypermedia to go ahead and load those. So if I click on any one of those, then it's going to trigger off a command, right? So that the state of that aggregate has to be in the correct state to be able to proceed forward. So this is a good example application. And then finally, we saw what CQRS looked like. You can use CQRS to create materialized views from a stream of events. So here I have my command and query side. So maybe I want to suspend an account. That's going to be a command. It's going to update the status in the database. And then on the query side, I'll have my account model, which has been updated. So I have my command service here, and that's going to write events again to the event store, just as a review. And then I'll have my event processor, which is going to have my collection of handlers. Now, depending on the type of the event handler will then process that event, perform an action to update the data store, and then you'll be able to query that from the query side. And then again, slapping an API gateway on it, and then you have kind of what I call a service block, which is a distributed application that's a microservice. So you can also add in serverless event handlers. So microservices can be event sources. So here's an example of that. I have a service core here, which is my Spring Boot application, and I also have all of my event handlers, which are processors, that are hosted on some serverless provider like AWS Lambda. So every time I get an event, I can go ahead and pass that along to the handler, and the handler can be polyglot, right? So if I want to use some machine learning library that's in Python, I can go ahead and have that Python handler get that event, perform a machine learning algorithm, and then update the query model. So we're going to have a project. We have a project that's in the works called Spring Cloud Function, which is going to allow you to run Spring Boot applications as serverless functions. That is not yet even really a project on the website. It's being created by Mark Fisher, one of our Spring Team engineers. And it's a very cool project. I've created an example application with it already, which will allow you to do something similar to this. But you'll just have Spring Boot functions. You won't need to have a JavaScript function or a Python function. So I'm a little bit early, so I think I'm going to do some other things. Do you have any questions so far? I can't see anything, but if you do have questions. Yeah, here. How will the system react if you need to add a new state? Yeah, let's check that out. So if I go back to the state machine here. So let's say that I want to fork from the reservation failed. So at reservation failed here, I can create another handler which will generate a command. And so I can expand this. The idea is I want to make sure that it arrives at some terminal state. So this state machine can grow and grow. And then if for some reason I've changed the state machine to the point where I need to reprocess everything, I can certainly do that. I can regenerate all my query models and use something like blue-green to be able to switch between them. So it depends on the level of change, but that's what I've seen so far. Any other questions? All right, so now I'm going to dance for a while because I'm early. So I guess what I'm going to do is show you some of the experimental stuff that I'm working on. So if I open up. So I have a GitHub project which is called Service Blocks. And this is an example of building a CQRS microservice that has those serverless event handlers. So if I drill into this, I'm going to have a set of functions, and those functions are going to be maybe an event handler, which is going to update a CQRS view. This is a GitHub, a project that takes in GitHub events, like commit events, and it's going to generate a view, like figuring out the tight coupling between files and a commit. And I think I can just open this up. CD. Oh, okay. All right, so here in my, oh, this is so old. So stuff like this happens when you're on stage. Like you're trying to update and it just says, make sure you have the correct access rights, which is no fun. So let's try that again. No. All right, so I can't even pull it, so I'm just going to walk you through it on GitHub. So if I go to, this is what a Spring Cloud Function application looks like. So I'm going to have, what changes with a Spring Cloud Function app is that you're going to have your Spring Boot application class. You're going to go ahead and define a bean here, which is going to be a function, and you specify what your event is. And so here I have my project event parameter. That's going to actually wrap around an event, and then I'm going to return back here. I'm returning a map, which is the result. And so here what I'm doing is I'm taking in that event from that serverless function, and then I'm going to go ahead and see whether or not maybe a commit already exists. And then I'm going to create a view processor, which is going to update that model, right? So I have this core application that's sending these events to a Spring Cloud Function app, which is serverless. And every time I send a request there, it's going to start up and it's going to process an event. It's going to write back to a MongoDB database, right? Because now I'm using Spring Cloud Function, I can just use Spring Data JPA, or sorry, Spring Data MongoDB, and I can actually reactively monitor for these events being processed by this function to update some view, to update some query view for the application. Now that's pretty much all the dancing that I can do right now. So I'm going to go ahead and ask for a round of questions, and then I'm going to call it. Any more questions? Okay, thank you guys. I have a website where you can find all these reference architectures. And so if you go to my blog, which is kennybastani.com, you'll be able to find all these reference architectures. You can run them on your own. So I just want to say thank you very much for coming today. I appreciate your time. Thank you.